All right, welcome back, linear algebra students. Today we're going to talk about section 5.2, orthogonal complements and orthogonal projections, and we're going to continue on to section 5.3 and talk about the Gram-Schmidt procedure. So to give you an idea of what I'm talking about when I say orthogonal complements, suppose we're living inside of R2, and I'm going to draw two subspaces here. So the first I'm going to draw in blue. It passes through the origin just like any subspace should, and I'm going to call it W. Now I'm going to draw another subspace in red, and I'm going to call it S. And I've drawn it as best as I could, but it's not perfect. But you should think of these two lines as intersecting in a right angle at 90 degrees. Now, suppose I look at a vector inside of W. It doesn't matter which vector I pick, so I'm just going to pick some vector, maybe call it X. And I'm going to pick a vector inside of S, and I'm going to call it Y. Now, because the subspace W and the subspace S intersect at 90 degrees, the vector X and the vector Y, because they come from W and S respectively, these two vectors are orthogonal to each other or perpendicular to each other. Or in other words, their dot product is equal to 0. Now, that's nothing special about the vector X and Y that I chose. I actually could have picked any vector inside of W and any vector inside of S, and the same would have held true. So for example, let's pick a vector, say, down here. I'm going to call it V. And I'm going to pick some vector inside of S, maybe something like this. And I'm going to call it U. And again, because the lines S and W intersect at 90 degrees, these two vectors are going to be orthogonal to each other. So U dot V is equal to 0. And hopefully you can see that if I ever pick a vector from W and a vector from S, these two vectors are going to be orthogonal to each other. So in some sense, we're going to think of the subspace W and the subspace S as being orthogonal to each other. As subspaces, we think of them as being orthogonal to each other. And in fact, we have a special name for this. So since S is in some sense orthogonal to W, we would call it the orthogonal complement of W, and we would denote it by W with this superscript upside down T, which we call W perp. So let's make this more precise. Let W be a subspace of Rn, then a vector U inside of Rn is said to be orthogonal to the subspace W if it is orthogonal to every single vector inside of W. So this is what it means for a single vector to be orthogonal to a subspace. It means that that vector U is orthogonal to every single vector you could possibly pick from that subspace. Now suppose we take all of the vectors U that are orthogonal to a subspace W and we put them in one giant set. Well, we'll call that set the orthogonal complement of W. Or in other words, the set of all vectors in Rn which are orthogonal to W is called the orthogonal complement of W and is denoted by W perp. So on this previous slide, we saw two subspaces in R2, both of which were lines, but these two subspaces S and W that we saw on the previous slide would be orthogonal complements of each other. Let's look at an example in a slightly higher dimension. So suppose now instead of being in R3 or in R2, we're talking about subspaces in R3. And suppose W is a line inside of R3. Well, what will W perp be in this situation? So let's draw ourselves a line in R3. Okay, so this is our subspace W. Well, what does the orthogonal complement of this look like? Well, notice it'll be a little bit harder to draw because now we're in R3. But notice I could pick a vector like this that is orthogonal to W. I could also pick a vector that shoots out this other side. That would be orthogonal to W. And really, any vector that sort of lives on this line is going to be orthogonal to W. But I could also pick vectors that sort of come out of the screen here. So it'll be a little bit harder to draw, but imagine this vector sort of still comes out of the screen, but is still orthogonal to W. Or I could have a vector that kind of shoots back into the screen, and that would also be in W perp. So all of these vectors that I'm drawing, and I can draw lots of them, all of these vectors here are in W perp. And in fact, hopefully you can kind of, by thinking about it for a minute, if we kind of erase the vectors for now, hopefully you can kind of convince yourselves that these vectors are actually going to form a plane. And this plane is going to intersect W right at the origin. So this plane is what we would call W perp. This is the orthogonal complement of W. And any vector in this plane, or the special thing about this plane is that any vector in this plane is orthogonal to any vector on the line. Doesn't matter which two vectors we pick. Any vector on the plane is orthogonal to any vector on the line. And that's what makes these two subspaces orthogonal complements of each other. Let's look at another example. Now, we're still going to be in R3, but now let's suppose that W is a plane in R3. So I'm going to draw a plane, W. What will W perp be? Well, a very similar argument holds here, like the one we used last time. So if W is this plane here, notice if I pick, what I want to do is I want to find the subspace where every vector in this subspace is orthogonal to every vector in W. Hopefully you can convince yourself that that subspace, W perp, is going to be a line that intersects W at the origin. And exactly the same like in the previous case, if I look at any vector inside of W and any vector inside of W perp, if I've drawn them carefully, these two vectors will be orthogonal to each other. So it's really the same example we've just seen twice. In one case, W was the line and W perp was the plane. In the second example, W was the plane and W perp was the line. But hopefully you can kind of see how these two subspaces are orthogonal to each other. Any vector inside of W is orthogonal to any vector inside of W perp. All right, let's look at a theorem that tells us something about orthogonal complements. So let W be a subspace of Rn. The first thing we can say is that the orthogonal complement of W is going to be a subspace of Rn as well. So to prove this one, we would just have to go through and check the three subspace criteria that we learned in Chapter 3. So we'd have to prove that the zero vectors inside of W perp. We'd have to prove that whenever we take two vectors inside of W perp and add them together, we get another vector inside of W perp. And we'd have to show that whenever we take a vector inside of W perp and we multiply it by a scalar, we again get a vector inside of W perp. The second thing we can say is that whenever we take a subspace, we look at its orthogonal complement, and then we look at the orthogonal complement of that subspace, we're just going to get the original subspace W back. So hopefully this was kind of clear from that first example, or rather the second example we saw. We had that subspace W, it was a plane inside of Rn, or R3. When we looked at the orthogonal complement, it was this line here. So this was W perp. Now if we look at the orthogonal complement of this line, we're going to see that it just happens to be this plane again. Or in other words, W is equal to the orthogonal complement of the orthogonal complement. The third thing we can say is that the intersection of W and W perp is just the zero vector. Or in other words, the only vector that lives in both W and W perp is the zero vector. And finally, the last thing we can say is a real lifesaver here. So let me explain what this is saying. Suppose that W is equal to the span of the vectors v1, v2, all the way up to vn. So remember, the span of these vectors is just the set of all linear combinations of them. So in other words, the subspace W is made up out of vectors that look like this. Linear combination of the v vectors. Suppose now I have another vector just called v, and I want to check whether this vector lives inside of the orthogonal complement. Well, in order for v to live inside of the orthogonal complement of W, it would have to be orthogonal to every single vector inside of W. Notice, however, there are going to be an infinite number of vectors inside of W. There are an infinite number of linear combinations I could cook up, and in order to verify that v lives inside of W perp, I would have to show that v is indeed orthogonal to every single linear combination of these vectors, every single vector inside of W. Now that's ludicrous. There's an infinite number of vectors. We're not going to sit around taking dot products all day. we have better things to do with our time. What this last part of the theorem tells us is that in order to check whether V lives inside of W perp, we don't have to check that it's orthogonal to an infinite number of vectors individually. We can just show that it's orthogonal to each of these spanning vectors. And if it happens to be orthogonal to each of these spanning vectors, then it's going to be orthogonal to every single vector inside of W. Like I said, that's a real time saver there. So I hate to take away some of the fun of proving these things from you, especially when you have a lot of time on your hands in home quarantine. So maybe I'll prove 3 and 4. Maybe I'll just prove 3, and if it's a lot of fun, we'll move on and prove 4. So to prove 3, we want to show that the only vector that lives inside of W and W perp is the 0 vector. So let's suppose that Z is in W and W perp simultaneously. Well then, since the vector Z is in W perp, it is orthogonal to every vector in W. That's what it means to live in the orthogonal complement. It means that you are orthogonal to every single vector inside of W. But the vector Z lives inside of W as well. So Z is orthogonal to everything in W, including itself. So in other words, we know that Z dot Z is equal to 0. But remember, Z dot Z is just equal to the norm of Z squared. So if we take the square root of both sides of that equation, this just tells us that the norm of Z is equal to 0, and the only vector that has norm or length 0 is the 0 vector itself. So in other words, Z, gotta draw my little arrows over top. In other words, Z is equal to the 0 vector. So if you, and sometimes proofs will make use of this fact. You'll try and prove that something has to be 0. So what you do is you prove that that this vector that you're interested in lives inside of W and inside of W perp. And since the 0 vector is the only thing that lives inside of both of those subspaces, you can prove that your vector has to be 0 that way. Well, that was a lot of fun. Maybe I won't prove 4 very formally. It's in the notes, so you can read up on that if you want. But just to give you an idea of how it goes, what we want to do is we want to show that if a vector V is orthogonal to each of these spanning vectors here, then it has to be orthogonal to every single vector inside of W, and hence it has to live in W perp. So here's just kind of a sketch of one of the steps. Suppose V is orthogonal to the vectors V1, V2, all the way up to Vn. Well then, if you pick some vector inside of W, say C1, V1 plus C2, V2, all the way up to Cn, Vn, we can show that the vector V has to be orthogonal to this vector by just taking the dot product. So if we take the dot product and we sort of distribute it through, we're going to get this is equal to C1V dot V1 plus C2V dot V2 plus CNV dot Vn. And now, because V was orthogonal to each of these spanning vectors, it's not too hard to see that the first term is going to be 0 because V dot V1 is 0, V dot V2 is 0, all the way up to V dot Vn is 0, and hence this is equal to 0. Therefore, the vector V is orthogonal to any linear combination of V1, V2, all the way up to Vn. And if V is orthogonal to any linear combination of these things, it's orthogonal to everything inside of the span, or in other words, it's orthogonal to everything inside of W. So that more or less proves part 4 for us. All right, so if you're anything like me, you're pretty jazzed from that theorem we just proved. So let's try and do another one. Let A be an m by n matrix. Well, associated to A, there's a row space and there's a column space. What are the orthogonal complements of the row space and the column space? Well, to try and illustrate that, let's do an example here. Let A be the following matrix. 1, 0, 2, -1, and 0, 1, 3, 1. Okay. Well, notice I'm going to give you a vector, x, which is equal to -2, -3, 1, 0. Notice that this vector, and it kind of came out of nowhere, so don't worry about where it came from right now. But notice that this vector is orthogonal to both of the rows of A. Okay, so in other words, if I take the first row of A, which is 1, 0, 2, -1, and I take the dot product with this x vector that I've pulled out of nowhere, -2, -3, 1, 0. Notice I'm going to get 0. And likewise, if I take the dot product of the second row, 0, 1, 3, 1, with our vector x, I'm going to get 0. Okay? So because x is orthogonal to both of the rows of A, and because the rows of A span the row space, that tells me that x is in the orthogonal complement of the row space. Okay? So remember, if we want to prove that a vector is in the orthogonal complement of the row space, we don't have to show that it's orthogonal to every single vector in the row space. We just have to show that it's orthogonal to a set of vectors that spans the row space. And the easiest set of vectors that spans the row space that we have are just the rows of the matrix A. So because it's orthogonal to both of the rows of A, it's orthogonal to everything inside of the row space of A. And therefore it's inside of row A perp. All right, well also notice that if we take the matrix A, 1, 0, 2, -1, 0, 1, 3, 1, and we multiply it by this vector x, -2, -3, 1, 0, well, what happens when we do matrix multiplication? Now again, there's a few ways to think of matrix multiplication, but the way I think of it is, if I want to figure out what goes in this top spot, I take the first row of the matrix A, and I take the dot product with the vector x. Well, the dot product of the first row with the vector x is just going to be 0. So I get 0 here. And likewise, if I want to figure out what goes in this spot, I'm going to take the second row of the matrix A, and I'm going to take the dot product with the vector x. And again, when I take this dot product, I get 0. So because this vector x was orthogonal to both of the rows of A, when I multiply the matrix A by the vector x, I just get 0, 0. Or in other words, the vector x is in the null space of A. Okay? So remember, whenever I have a vector and I multiply it by a matrix and I get the 0 vector, it means that this vector here lives inside the null space. So hopefully, if you think a little bit carefully about this, really we're just kind of seeing the same thing but from two different perspectives. If the vector x is orthogonal to both of the rows, then that means it lives in row A perp. On the other hand, if it's orthogonal to both of the rows, that means when I multiply by the matrix A, I'm just going to get 0, 0, and hence x lives inside the null space. So what this tells us is that the orthogonal complement of the row space is really just equal to the null space. Now what about the orthogonal complement of the column space? Well, we can actually just use this fact here to tell us what this has to be. Remember, the column space of A is just equal to the row space of A transpose. So if we take the transpose, we turn all our columns into rows and rows into columns, and therefore the space that's spanned by the rows of A transpose is the same thing as the space spanned by the columns of A. Now, if we want to look at the orthogonal complement of these things, the orthogonal complement of this is equal to the orthogonal complement of this. But if we use this fact right here, where instead we replace A with A transpose, this is going to tell me that the orthogonal complement of the row space is really just equal to the null space of A transpose. And that's exactly what we get here. Okay? So it turns out that these subspaces are important for any matrix, and so we give them a special name. We call these subspaces the fundamental subspaces of A. In other words, the row space, the null space, the column space, and the null space of A transpose are the fundamental subspaces of A. All right, so this is a great theorem, and it's going to come in handy in a lot of situations when we're not even thinking about a matrix. So here's an example. Let W be the span of these two vectors. Let's find a basis for W perp. So to solve this problem, we're actually going to do something kind of clever, like we always do. Let's take the vectors. So these two vectors span W. Okay? We're going to take these two vectors, and we're going to put them as the rows of a matrix. Okay, so A is going to be the matrix 1, 0, 1, 1, and 1, 1, 0, negative 1. Okay? Now, the reason we did this is because if I just give you any old subspace here, we don't really have any tools for finding the orthogonal complement of W. Okay? But by taking these two vectors and putting them as the rows of a matrix, now we're able to identify the subspace W with something we recognize. Or in other words, so W, which is the span of these two vectors here, so 1, 0, 1, 1, 1, 1, 0, negative 1. By definition, W is just the span of these two vectors, but these two vectors are the rows of the matrix A. So the space that's spanned by the rows of the matrix A is the row space of A. All right, so you can maybe now see why we wanted to do this. By putting these vectors as the rows of a matrix, now the space that we were asked to consider, which was W, the span of these two vectors, that's just the same thing as the span of the rows of A, and hence W is just equal to the row space. Now the reason we wanted to do this is because we know what the orthogonal complement of a row space is. So we have W equals row A, and if we take the orthogonal complement of both of these, well, the orthogonal complement of the row space is just the null space. So in other words, the original question we were asked was to find a basis for W perp. What we've done is we've converted this into a question about finding a basis for the null space of A. And we definitely know how to do that. So let's go ahead and do that. Let's take our matrix A, 1, 0, 1, 1. We're going to row reduce. And when we row reduce, we get 1, 0. We get this. So remember, we kind of think of this as like secretly being an augmented matrix with zeros over here, even though we didn't write them down. And so that top line is going to give us x plus z plus w equals 0. Second row gives us y minus z minus 2w equals 0. And if we rearrange these solving for our leading variables, we get x equals minus z minus w and y equals z plus 2w. So if we take our vector x, y, z, w, and replace our leading variables with these expressions for our free variables, we can split them up like we normally do, and we get this vector here, and this vector here. Okay. Now, normally, we would think of these two vectors as being a basis for the null space, okay? The null space of the matrix A. However, the null space of the matrix A is just the orthogonal complement of W, so by finding a basis for null A, we've really found a basis for the orthogonal complement of W. And that answers our question. Okay, now the nice thing about these questions is that if you're unsure of yourself, you can always take these two vectors that you found, and you can take the dot product with the vectors that you started with. And of course, you should get 0 in both cases. All right, so let's shift gears now for a minute and talk about orthogonal decompositions. And the main idea behind this topic is the following theorem. So let W be a subspace of Rn. Then if I give you any vector y inside of Rn, you can always split the vector y up into two pieces. The first piece is what we call the orthogonal projection of y onto W, and the second piece is what we call the orthogonal component of y with respect to W. Now the special thing about these two vectors or these two pieces, is that the projection of y onto W is a vector inside of W, and the perpendicular component of y with respect to W is a vector that lives in W perp. Now, one thing I didn't point out is that we can take a vector y and we can split it up into these two pieces. One piece that lives inside of W and one piece that lives inside of W perp. And there's only really one way to do that. There's only really one way to split the vector y up into a piece that lives in W and a piece that lives in W perp. Now, how do we figure out what these things are? We're going to talk geometrically about what these are in a minute, but you should think of this as really corresponding to, we've seen orthogonal projections onto lines before. This is really the same thing, but where instead of just projecting onto a line, we're going to be projecting onto something that's possibly higher dimension, like a plane or some higher dimensional subspace. So how do we figure out what these two pieces are if I give you the vector y and I give you the subspace W? Well, the way we do this is, first of all, we need to have an orthogonal basis for our subspace W. If we have an orthogonal basis for our subspace W, then we can compute this projection piece here using this formula right here. Now this formula might look kind of familiar if you look at these different pieces, and we'll talk about why that is in a minute. So that tells you how to find the projection piece. The way that you find the perpendicular piece is you just take the original vector y and you subtract off the projection piece. So this gives us a way to sort of split a vector y up into a piece that lives inside of W and a piece that lives inside of W perp. And we can figure out what these two pieces are by using this formula here for the projection piece and this formula here for the orthogonal piece. Now, we're going to see some examples, and I will talk about sort of geometrically what this means in a second, but I do want to give one important warning. And that warning is that in order to figure out what this projection piece is, you really have to start with an orthogonal basis. If you start off with a basis that's not orthogonal, then this formula won't work. Okay, so you've been warned. All right, let's see if we can understand what's going on by way of a picture. So in this picture, let W be the blue plane. It's going to be the subspace we care about. Y is going to be a vector that points outside of W, and then inside of W we have two basis vectors, U1 and U2. Now, you'll notice that U1 and U2 are orthogonal to each other, and that's going to be really important for what follows. So you definitely want to start off with an orthogonal basis, or the rest of the stuff I say here is not going to hold true. So even though the vector y doesn't live inside the plane, what we can do is we can find a vector that does live inside the plane that gets as close as possible to the vector y. Now, the way we would find such a vector is we would start at the vector y, and we would draw a line down to the plane that intersects the plane in 90 degrees. And if we do that, then the place where the line intersects the plane is going to be this red vector here. And that's the vector that gets as close as possible to y inside the plane. So we call this vector the projection vector of y onto the subspace W. Now I want to show you why the formula that we had on the previous slide actually gives us this projection vector. So here's the idea. Instead of projecting directly onto the subspace W, what we're going to do is we're going to project onto the two basis vectors first. We're going to do orthogonal projection onto these two basis vectors first. So let's take the vector y. Let's project down onto the vector u1. That gives me this blue vector here, this blue vector which is the projection of y onto u1. And then I'm going to do the same thing projecting onto u2, and that gives me a second vector, a second blue vector here. Now if I take these two blue vectors and I add them up, that's going to give me this purple vector here, and this purple vector here is exactly the vector I would find if I dropped a line down from y to the plane so that it meets the plane orthogonally. So this is exactly what I said would be the projection of y onto the plane W. Now there's another piece that's kind of lurking in the background here, and that's the orthogonal component. So if I take the vector y and I subtract off of it the vector projection of y onto W, it's going to leave behind this vertical piece here, the orthogonal component of y with respect to W. Now this piece, this orthogonal component, is going to be perpendicular to the plane W. Or in other words, this piece here is going to live in W perp, while the projection vector lives inside of W. So this kind of explains for us why that formula we saw at the very beginning actually works. So let me flip back to it. So this is the formula that we saw at the very beginning, this projection formula here. Okay. Now if you notice, the first term in the projection formula is exactly the formula for the projection of the vector y onto u1. And likewise, all of the other terms in this formula are just the terms you would see if you wrote down the projection of y onto the uj basis vectors. And so this corresponds to the idea that instead of sort of projecting directly down onto the plane W, we can instead project onto the individual basis vectors and then add them all up at the end. All right, let's look at an example here. Let W be the span of u1 and u2. What we want to do is we want to take the vector y and we want to split it up into the sum of a vector that lives in W and a vector that lives in W perp. So first of all, we want to use that formula that we saw on the previous slide. In order to do that, we need to make sure that we have an orthogonal basis for our subspace W. So we really ought to check that u1 and u2 are orthogonal to each other. So we're going to check that u1 dot u2 is equal to 0, and it's easy to see that that is in fact 2, and so hence we can use the projection formula from the previous slide. Okay, so this tells us that the projection of the vector y onto the subspace W is given by u1 dot y over u1 dot u1 times u1. Okay, so remember this first piece is just a scalar plus u2 dot y over u2 dot u2. Okay, and so this piece is another scalar, and we're multiplying it by the vector u2. So when we actually plug these things in, u1 dot y is going to be 3 over u1 dot u1, that's going to be 2, times the vector u1, and then plus u2 dot y is going to be 7 over u2 dot u2 is 2, and times u2 is 1, 0, negative 1. And when we add these up, we get 5, 0, negative 2. Okay, so that gives us the orthogonal projection of the vector y onto the space spanned by u1 and u2. Now we want to find the orthogonal component. So the orthogonal component, the way we find that is we just take the original vector y and we subtract off the projection vector. So 5, 7, negative 2 minus 5, 0, negative 2, and that just leaves us with the vector 0, 7, 0. Okay, so what this tells us is that we can take the vector y and we can split it up into two pieces, the projection piece of y onto w and the orthogonal component with respect to w, and those two pieces are 5, 0, negative 2 and 0, 7, 0. Okay, and this first vector is in w, the second vector is in w perp. Now I do want to emphasize that this decomposition is unique. Okay, so if I give you a vector y and I suppose I've broken it up into one piece that lives inside of w and one piece that lives inside of w perp, well, the only way for you to do that is if the first vector is the projection onto y and the second vector is the orthogonal component. So that's what this theorem right here sort of emphasizes, is that if w is a subspace of Rn, v is a vector inside of Rn, then there is a unique vector w and a unique vector w perp, so that v equals w plus w perp, where w lives inside of the subspace w and w perp lives inside the orthogonal complement of w. So this is really kind of the same theorem that we saw when we had that projection formula. It's just stated a little different. There's two other theorems that will be kind of important. The first is that if w is a subspace of Rn, then the dimension of w plus the dimension of w perp equals n. So in other words, the dimension of a subspace and the dimension of the orthogonal complement has to add up to the total dimension of the space. So in one of the earlier examples we saw, where w was a plane, we saw that w perp was a line. And so in this case, the dimension of w was 2. The dimension of w perp was 1. And when we add these up, we get 3. And that's what we would expect to get because our vectors were in R3. Okay. On the other hand, if my picture was in R2, like the first one I drew, and my subspace was a line, w, then the orthogonal complement is another line, w perp, and that makes sense because the dimension, in this case, the dimension of w plus the dimension of w perp is just, this is 1, and when we add them up, we get 2, and that makes sense because we were in R2. So whatever the dimension of the space you're in, whenever you take a subspace w and its orthogonal complement w perp, the dimension of those two subspaces has to add up to the total dimension. We can use this theorem to reprove the rank theorem. So remember, if A is an m by n matrix, then the rank of A plus the nullity of A is equal to n. So let's think about why this is true in light of the things we have. Well, remember, the rank of a matrix A is just the dimension of the row space of A. Likewise, the nullity of A is just the dimension of the null space of A. Okay? But remember, the null space of A, we saw that is equal to the orthogonal complement of the row space. So really what this formula is saying is the dimension of the row space of A plus the dimension of the orthogonal complement of the row space of A is equal to, well, it should be equal to the total dimension of wherever the row space lives. But remember, the row space of A is a subspace of Rn. So the dimension of the row space plus the dimension of the orthogonal complement of the row space should add up to n, because they both live inside of Rn. And that's exactly what the rank theorem tells us. All right, so that does it for section 5.2. We are going to move into section 5.3. Now, in a typical year, we would cover all of section 5.3. Some of you may have noticed that this year is not shaping up to be quite so typical. So because we lost a class due to the coronavirus class cancellation, we are not going to be able to talk about QR factorizations, but we will still talk about the Gram-Schmidt process. And this is an important thing for the singular value decomposition, which is coming up. So it will be important that we talk about this. But to understand why we need the why we need the Gram-Schmidt process, if you think back to section 5.2, which we talked about like 7 or 8 minutes ago, you'll remember that if you want to take a vector y and project it onto a subspace W, you have to start off with an orthogonal basis for W. Now this is just one example of a situation where you want to do some kind of calculation, but in order to do so, you need to have an orthogonal basis. The problem is that if you bump into a basis on the street or you meet a basis at a party, typically speaking, that basis is not going to be orthogonal. So what you'd like to be able to do is take a basis which is not orthogonal and convert it into a basis that is orthogonal without changing the space that that basis spans. So let's make things a bit more concrete. Suppose you have a basis x1, x2, all the way up to xp, and it's a basis for some subspace W. Well, if x1 through xp are not orthogonal already, is it possible to modify them so they become orthogonal in such a way that you don't change the fact that they span W? Well, let's try and understand this with a picture inside of R3. So to make things really concrete, let's start off with two vectors, u and w, inside of R3. Suppose they're not orthogonal to each other, and suppose that they span a plane inside of R3. All right, so here's the picture. We have our vector u, we have our vector w. These vectors are not orthogonal, but they do span the plane here, which I've drawn in blue. Okay. Now, because u and w are not orthogonal, what we want to do is we want to take one of them and modify it so that it becomes orthogonal to the other one. So for example, let's take the vector w. Now, if we look at the vector u, it spans a subspace, which is just a line right here. Okay? And if you remember from the previous section, if you have a vector w and you have a subspace like the one spanned by u, you can always take w and you can split it up into two pieces. The first piece is parallel to the subspace, or rather it lives in the subspace, and that's the projection of the vector w onto the line spanned by u. The second piece is the orthogonal component of the vector w with respect to the subspace spanned by u. So what we've done is we've taken the vector w and we've split it up into one piece that's parallel to u and one piece that's perpendicular to u. And what we do is we throw away the piece that's parallel to u and we just keep the piece that's orthogonal to u. And by throwing away, what I mean is we take the vector w and we subtract away from it the projection of w onto u. So we're taking this vector, we're subtracting the parallel piece, and what's left over is this piece that's orthogonal. So what that does is if I keep the vector u and then I replace the vector w with this piece, what I've done is I've obtained an orthogonal basis for the subspace I care about. Now, it's easy to see what we do for two vectors, as I've illustrated here. What if we have three vectors or four vectors or more? Well, to illustrate that, let's draw a third vector in here. I'm going to call it y. All right? So if we have three vectors to start out with, what we're going to do is we're going to ignore the third vector for now, and we're just going to modify the first two vectors like I described a minute ago. So in other words, I'm going to color them in purple. We're going to take the vector u, we're going to leave it exactly as is. It's perfect the way it is. So why are we going to try and change it? We're not. Okay? So we leave the vector u as is. Now the vector w is not orthogonal to the vector u. So as we explained earlier, we're going to take the projection, we're going to subtract it away from the vector w, and what that'll leave us with is it'll leave us with this orthogonal component. Okay. And that's the second vector that we're going to take in our set. Now we move on and we look at the third vector. It is not orthogonal to the previous two vectors, this one and this one. So we want to somehow make it orthogonal to these vectors. So what we do is we do exactly the same thing. We would take the vector y, we would project it down onto the plane spanned by our first two vectors, and then we would take the orthogonal component of that projection. And that's the vector I've drawn right here. So it's that orthogonal component of y that we would hang on to. Okay. Okay. And you'll remember we find this orthogonal component by taking the vector y and subtracting off of it the projection of y onto this blue plane here. So we kind of repeat this procedure again and again. We start off with the first vector, we leave it the same. The second vector, we take the second vector, then we subtract off of it the projection onto the first vector, and that makes it orthogonal to the first vector. Then we take our third vector, we subtract off of it the projection onto the space spanned by the first two vectors, and that makes it so that it's orthogonal to the first two vectors, and we rinse and repeat. So this is called the Gram-Schmidt procedure, and here's the formula for doing it. So if we have some basis, x1, x2, all the way up to xp for our subspace W, then we can convert it into an orthogonal basis as follows. So our orthogonal basis is going to be v1 through vp, and the way we figure out what the v vectors are is, well, our first v vector, so v1, is just equal to the first vector in our original basis. Now our second vector in our new orthogonal basis is going to be obtained from the second vector in our original set, but we subtract off of it the projection of the second vector onto the first v vector. So by doing that, we're taking x2 and we're modifying it so that it becomes orthogonal to v1. And that becomes the second vector in our orthogonal basis. Then to find the third vector in our orthogonal basis, we take the third vector in our original set, we subtract off of it the projection onto v1 and the projection onto v2. And what this does is it takes the vector x3 and it makes it so that it's orthogonal to both v2 and v1. So what this does is we sort of by sort of repeating this procedure, we're taking one vector at a time and we're making sure that it's orthogonal to the vectors we've already looked at. And if we do that for our entire set, then we'll end up with an orthogonal basis. So let's see an example. Here are three vectors, x1, x2, and x3. They span a subspace of R4. We're going to find an orthogonal basis for this subspace using the Gram-Schmidt procedure. Then after finding an orthogonal basis, we're going to turn it into an orthonormal basis. So we have our x1, x2, and x3. Let's start computing our v1, v2, and v3. So if we look back to that formula, what it tells me is the first vector just stays the same. Okay, so v1 is just equal to x1. All right. Then v2, according to the formula, is just going to be x2 minus x2 dot v1 over v1 dot v1 times v1. And that's going to be x2 is just this minus, so we're doing the dot product of x2 with v1, so that's going to be 1 minus 2 is minus 1 upstairs, and then downstairs we have v1 dot v1, so that's going to be 1 plus 1 is 2, 3, it's going to be 7. If I'm so bold as to wager a guess. And then we multiply that by v1, which is 1, 1, negative 1, and 2. And ignore the shuffling of paper. I'm just going to compute the answer in my head. I believe this ends up being 8 over 7, 1 over 7, negative 1 over 7, and negative 5 over 7. All right, so continuing on, in order to compute V3, according to our formula, we take x3, and then we compute the projection of x3 onto V1, which is V1.x3 over V1.V1 times V1, and then we subtract off the projection of x3 onto V2. Okay, so x3 is 0, 1, 1, 1, minus x3 dot v1 is going to be 2 upstairs. Downstairs we've got v1 dot v1, so again that's going to be 7. And then this term is going to be v2 dot x3, so we take our v2 dot x3, that's going to give us negative 5 over 7 upstairs. And downstairs we've got v2 dot v2, which is going to be, so this is going to be a bit of a beast. So right down here we're going to get 49 because of the 7 in the denominator. Then we get 8 squared is 64, plus 1 squared is 65, 66, plus 25 is 91, I believe. Times this, so that's times v2, which is 8 over 7, 1 over 7, negative 1 over 7, negative 5 over 7, and if we add this up, we get 2 over 13, 10 over 13, 16 over 13, and 2 over 13. Okay. Now, the nice thing is you can always check your work. So in the end, the 3 vectors I get here should be orthogonal to each other. And I'm not going to check them, but I think if you check them, you will see that they indeed are orthogonal to each other. Now, the last part of this question was asking us to find an orthonormal basis. Well, we already have an orthogonal basis. The only thing left to do to make it orthonormal would be to normalize this basis. Now, just a word of advice. If you are trying to normalize the basis, remember that involves taking the vectors and then dividing them by their length. Normalizing a vector like this is going to be kind of ugly to do because it has a denominator. So you can kind of do it in 2 steps to kind of make your life easier. For example, here, you could take this vector, you could multiply it by 13, and that would give you a new vector. And that new vector would be just a rescaling of the original vector you found. But you might find that that's a lot easier to normalize than it would be to normalize this vector here with the weird denominator it has. It works because if you multiply by 13, all you're doing is you're making it longer, but then in the end you're just going to be normalizing it anyways. So it just might save you the possibility of making a few algebra mistakes. But if we go ahead and we take each of these 3 vectors and we divide them by their length, what you're going to find is you're going to get, so here's the answer that we should have got. And I think that's what we got. And then if you want to normalize these vectors, so these are the vectors we found on the previous slide. If you want to normalize it and make each of these vectors have length 1, you just divide each of them by their length, and you get something that looks like this. All right, so this procedure is always going to work. If I give you a basis that doesn't happen to be orthogonal, you can always do the Gram-Schmidt procedure and you'll end up with an orthogonal basis. So this will be something we need to do a lot when we talk about singular value decompositions. All right, so the rest of the section is all on QR factorizations, but like I said, we're not going to talk about that. So we'll end here, and then the next class we will talk about orthogonal diagonalization.